So we're starting with a definition that you already know, but we're talking about radians. Has anybody already researched or read about radians or heard about radians? Anybody? It's nice people, okay, you kind of know, have heard of them, but maybe you don't really know what they are, but you've heard of them. Not really though. Okay. So up until now, you have measured angles in degrees. By definition, there are 360 degrees in a circle. Why 360? Why? Did you ever ask that question?
Because it goes all the way around.
But we just came up with, but couldn't you make that 1,000? Like, so why 360? You're right. It's funny. It's actually already part of your thinking of a circle is that it is 360 degrees. But is that not made up? Like, where did that number come from? So that's my first question. Why? Why 360? Any guesses? I'm not expecting you to know, but do you want to guess?
There's 4 right angles.
But why is a right angle 90?
It can be divided a lot of ways.
Where'd you get that from?
I think I've seen something about that.
Okay, very good guess. You might actually be onto something there. So if you didn't hear that, it can be divided by lots of things. 36, the number, has a lot of factors. It's divisible by lots of things. And so 360 is divisible by even more things, if you think about it. Yep. Other thoughts? Here's another common sort of guess. How many days are there in a year? $365. So not 360, but close, so they rounded. I don't know. Some people think that. Why would that be? Well, that's sort of the Earth going around the sun once, so it's a circle, right? It's not a perfect circle, it's an ellipse. But anyway, you get it. People think that might be the reason. I don't know that it has anything to do with that. I think it is actually closer to what Liam was talking about. But there's more to it than that. Ancient societies who did a lot of work in math had a base 60 system, so we have a base 10 number system. Base 12 or base 60, some people argue are better because they're divisible by lots of things. So 12 is divisible by more things than 10, so it's maybe arguably better. 36 is divisible by lots of things. 60 is kind of divisible by lots of things. So, I mean, this is all speculation. The real answer is I don't think we really know. But it might have something to do with that idea that some ancient civilizations had a base 60 number system. Base 60 is not ideal because literally you have to have a different character for every number up to 60 before you rotate back around to like a 1 and a 0. You know what I mean? So, and they did, like their pictures were like drawings, or their characters were like drawings of faces and stuff, or different things. Like it wasn't like a 1 and a 2 the way we think of it. It was like complex characters. Not efficient, not ideal, and having to memorize all of those and 60 different characters is not ideal. So having a smaller number of characters is kind of better, so 10 kind of works. 10 is the number of fingers that we have. Some people think that's why it's 10 is the system that we settled on. Intuitively, you might think 10, base 10 system, our main number system is based on it, is because, well, that's when you get a 1 and a 0. Well, no, you get a 1 and a 0 at 10 because we picked 10 as the base, right? Like, so you might be getting things backwards if you don't really think about it. Anyway, why do we have 60 seconds in a minute? Why do we have 60 minutes in an hour? Well, again, probably from those ancient civilizations, and they had a base 60 number system, so they chose 60. Why is the metric system base 10? Because that's the base we use now, and we designed the metric system to work that way, right? So asking these questions is interesting. I think in the case of 360, we don't have an actual answer, but I think most people kind of accept it has something to do with 360 is a nice number that's very divisible, and it's a multiple of 60, and so those things kind of make sense and fit together. At any rate, it is arbitrary. The degree is arbitrary. It makes sense to you because you've grown up using it. But what does it actually mean? We think of 360 degrees in a circle, but what's 1 degree? We often don't think about that. So, which is interesting because compared to measurement, I'm going to talk about this more in a minute, but compared to like measuring lengths, we kind of did it the opposite way. So For 360, we took the circle. We said 360 was going to be our divisor. And we figured out what 1 degree is by cutting up a circle into 360 equal segments. One of those segments is 1 degree. We don't often think about that or talk about that, though, right? We talk about 30 degrees or 38 degrees, and it's an angle. We don't think of it as 38 multiples of a single degree, which is by definition a circle cut into 360 equal segments. And that brings me to, what is any unit of measurement? Like, so we're going to talk about radians, and it's just a different way of measuring angles. But again, you don't think of a different way of measuring angles, and that doesn't even make sense because you just measure angles with degrees. It's just how you've always done it. It's what you do. What's an inch? About that much. What's a centimeter? It's about that much. What's 10 inches? About that. What's 10 centimeters? About that. Right? Like, you know, like you're comfortable with the fact that a centimeter, 1 centimeter is smaller than 1 inch, and there's a conversion factor between them, and maybe you're measuring a length of something, a piece of wood, in inches, or maybe you're measuring it in centimeters. You're comfortable with that, and yet we think, no, but angles are just measured in degrees. But a degree is just a certain amount of rotation, a very small amount. A circle's cut into 360 equal parts. It's small. And 30 degrees is just 30 of them. But what, can't you have a different unit of angle measurement? Could you cut a circle into 10 equal parts? So base 10 number system? Yeah, why not? Right? So that's what a radian is. It's a different type of measurement. Just like centimeters and inches, or yards and meters, or miles and kilometers. And again, you've probably heard the jokes, seen the jokes, and your other teachers have talked about this in other years, that the imperial system makes no sense, right? You've got 12 inches in a foot, 3 feet in a yard, however many yards in a mile. Like, it's ridiculous all over the place. Whereas the metric system was designed with math and sensibility in mind. Everything is a multiple of 10, and it makes more sense. So when I said before, how was the metric system designed? Well, you know, they came up with what a centimeter is, and then they said 100 of those makes up a meter. They probably came up with the meter first as their base unit, but anyway. And then everything is relative to that, compared to imperial, which seems like a mishmash of all kinds of different things, right? But the metric system picked a unit and then multiplied and divided to make things bigger or smaller from there, right? And did everything base 10 because that's our number system. So it kind of makes sense. But again, like I said, the different units of measurement in lengths or weights, kilograms and pounds, that's something you're used to. It's annoying to have to go back and forth, but it's something that you're used to. But you've never seen that in angles before, so it's different. There's 3 common ones on the planet. I think there are others that are used in very niche, maybe, or like it might only be one other, but in niche circumstances. But the 3 common ones, and the 3 ones that your calculator does, are degrees. Calculator by default is in degree mode. So back in grade 10, your teacher might have talked about this, but when you're doing triangle trig, you have to be in degree mode. And same thing in physics, when you're doing trigonometry, you want to be in degree mode because you're measuring things in degrees. So your calculator has to be in that mode. But I remember even like back in high school math, your teacher wouldn't tell you how to change the settings to put in degree mode. They just say, turn your calculator over and put a pin in the reset button, and that will turn it back to degree mode because that's the default, because that is the most common at a younger age. But then now you have to start working in radians. Not really today, but tomorrow we'll talk about how to change your calculator into radian mode, because you will need to change that. But your calculator has 3, so it's got degrees, which is randomly, well not randomly, but like whatever, arbitrarily, or somewhat with some kind of rationality, is split into 360. There's another one called gradients. G-R-A or G-R-A-D or G, depending on your calculator. You get that little symbol in the top that tells you what mode you're in. Anybody know what a gradient is? Again, you might have read about it it comes up usually if you're reading posts on this stuff. So gradient takes a circle and cuts it up into 400 equal parts. Why 400? Anybody want to guess? I think it's used in some kind of surveying or something like that. I've never actually used it. So 400 in a full circle makes a right angle 100. Space 10, so it kind of makes sense. So that's sort of where that one comes from. It's similar to 360, but not the same, and but has a little bit more sense in our number system. And then you have radians, which is the right one, but it's just a little bit trickier. Well, I'm going to talk about that more, obviously, as we get into this, but it's a little bit trickier at first, so that's why you don't tend to use it. And you're already familiar with degrees from elementary school, and protractors are in degrees, and it's kind of the way that you just start learning it. And they're just kind of whole numbers, so it's easy, whereas radians involve fractions, and obviously elementary school kids can't really do the fraction math that it's involved, so that's why they stay away from it until you get to grade 12, in Ontario at least, where all of a sudden now you have to learn this new unit of measurement. But don't ever think it's anything except for the difference between a centimeter and an inch. That's what it is, right? A centimeter and an inch are different units of measurement of the same thing. How far have I run? How far have I walked? How long is this board? It's a certain number of centimeters, it's a different number of inches, but it's the same length. Same thing with this unit of angle measurement. Okay, and there's a reason why radian is the right one to use, and it's the best one to use, that you may or may not agree with, and you may or may not see the value of it. I'm going to talk a little bit more about that today, but right now, really, it is your job just to learn it. Okay, but again, it's funny how your intuition or your gut, because you've only ever used degrees as that's the right way of doing things, and it makes more sense. And most of you or all of you may have some moment you're like, why are we doing this? Degrees were fine. Why are we complicating it? You got to obviously realize that people that have come before us and are much smarter than any of us, at least way smarter than me, I can't speak to you, have discovered that it is way better. And once you do a little bit of calculus, you would see for sure why radians are better. So, radian is a different way of measuring angles. It's a different unit. Just like an inch is bigger than a centimeter, a radian is much bigger than a degree. We're going to talk about that. That's the first thing we're going to do with those pictures of circles. It's useful because it has no unit. It's actually useful sort of for a more complex reason. But it's not a arbitrarily defined unit. So that's what it means by it has no unit, is it's naturally defined, not arbitrarily defined, like cutting a circle into some number, like 360 equal parts. It is a ratio of the arc length of a segment of a circle to its radius. So it comes from the relationship of an angle in a circle and the arc length that that angle defines, or vice versa. The arc on a circle and the angle, we call that subtended, don't worry about that word, by the arc of on a circle. Okay? So it has to do with that relationship, which is what we're going to explore quickly there. And it means that it has plagued high school math students all over the planet. I say that because it does involve fractions. This is the first time that you are actually going to be challenged to understand fractions and work with fractions at a deeper level, which is hard at first, but you're actually going to get really good at it. And for the first time in your life, you might actually be good at fractions and not be scared of them anymore. But it's really useful to mathematicians and physicists. So in physics and in math, and particularly calculus, is where radians shine. If you try to do calculus, which physicists in physics, they do a lot of calculus, and obviously engineering is based on physics and stuff, and we're going to do calculus next semester, those of you that are participating in that. We won't ever do it in degrees, so you wouldn't really see the alternative, but if you did it in degrees, it would just be more annoying. Okay? So there would be this little annoyance that you had to deal with every single time, whereas if you do everything in radians, which is what you do, it makes your life a little bit easier. Okay? Any questions so far? So, I mean, that's not that hard to understand, that it's a different unit of angle measurement, but then how do we actually use it? And by the way, I'm going to say this over and over and over again. From now on, today it's kind of okay because we're trying to learn what a radian is, and we're going to do that by comparing it to degrees. But after this, nothing we do is allowed to be in degrees anymore. So we're going to talk about converting today. And I will refer to it. I'm allowed to because I get to do what I want, I guess. But I will refer to it a little bit for your benefit. But on quizzes and tests, you are not allowed to do anything in degrees. You are not allowed to convert to degrees, do a question, and convert back. I will mark it wrong if you do that. If you do that on scrap paper or hide it from me or do it in your head, I can't stop you. But trust me, if you do things properly by the end of the unit, you won't have to do that. Even by next week, you won't have to. But that's not what we're doing. So even though today we're focusing on converting, that's just because we need something to do today. We can't really get into trigonometry without taking a day to sort of think about this. So that's why we're doing that. But moving forward, converting is not what we do. We just work in radians. And I would say by the end of this weekend, so like I said, tomorrow and the next day, we're going to be doing trig in radians. And then you have the weekend, luckily, but let's say even a few days to continue working with radians. And by the end of that, you need to be just understanding radians and doing the work in radians. Okay? It's a funny thing. I don't think I've used this analogy yet. It comes up twice in this course. I think it's a neat analogy. How many people know more than one language in here? It's often most people these days, which is interesting. Yeah. So something happens, and again, I would hope that your teachers taught you this, but if you learned it at a young age, your teachers probably, you weren't reflective enough to think about this, so your teachers probably didn't talk about it. It's an interesting thing that happens when you learn a new language. When you first learn, so let's say like in Ontario, if your primary language was English and then you were in French, I'm going to use that as an example, but obviously the same is true for any language, but that's a common thing that happens here in this part of Ontario, so you know that might be what some of you went through. When you first start learning French, what do? Everything is converted to English or your native language or your favorite language, whatever. You think in that language, so you would be thinking in English, you'd formulate your response in English, you'd convert that back to French or whatever language you're working in, and then whether it's oral, you're speaking it, or it's written, you're writing it down, you would have you develop your answer that was translated from the language that you're most comfortable in to the language that you're supposed to be working in. Part of becoming fluent in a new language, that doesn't happen anymore. So if you are fluent in a new language, and a lot of you can reflect on this and think about it, or if you're in French immersion and you became fluent and bilingual in French, and I did French immersion in high school, so I remember back in the day, not anymore obviously, but back in the day this did happen. You stop translating to English. You just start thinking in French. When you're in French class, you're thinking in French, right? And you're not like busy translating back and forth. Somebody asks you a question, you just understand what they're saying, and when you respond, you just do it in French. You don't have to translate back. And in particular, more of you who learned a different language other than English, but now are fluent in English, more fluent than most of us ever would be in French, you'd probably do that. You flip-flop back and forth when you're in English at school and when you're at home in a different language. You're thinking in English. You're not constantly translating back into your primary language or your first language. So it's an interesting analogy because that's what will happen here. At first, it will be very normal for you to translate radians back into degrees and always thinking about a couple of these pivot points or anchor points that are related between radians and degrees. But by the end of this unit, and I would hope for most of you, even by sort of Tuesday of next week or mid next week, you won't be doing that anymore. You'll just kind of understand radians. And in fact, when I have to do stuff like yesterday in degrees, it's harder for me because I don't tend to teach grade 11, so I don't do this stuff in degrees. Like I do triangle trig in degrees, but that's different. Whereas everything that I do, angles and standard position, is always radians, so it's actually easier for me than degrees. I tend to think that way. And I find myself sometimes doing it in radians in my head and having to convert back to degrees because that's just what I'm more used to. So it's really a matter of what you're used to, and you will get there even if it doesn't seem like it at first. But I have found with like anybody who tries, anybody who does the homework and works through it and tries to not be converting, you get there. You do eventually get there, okay? And I've got a few little tricks that I'm going to share with you today that really, really help to start to understand how radians work and the easy way of working in radians. And when we get into graphing next week, we start really counting in fractions and radians, and you actually get very good at it. Like I said, even doing some fraction math, you start to get really good at it. So it's kind of interesting. It's kind of actually neat. So, that was a big spiel. What the heck do we mean by ratio of arc length to radius? So, let's zoom in here. Where's the radius? That or that, right? They're both radius. So, if I started here and I rotated this way, I did rotate a certain angle, theta. Theta in degrees is something, I don't know. In radians, it's something else. I don't know. It's not the point of this. What's the arc length? We're going to call that A. Would you say A, just visually, is bigger or smaller than R in that diagram? Should be an easy question. Help me out here. Smaller. So would you do that? Yes? Radius is always positive, correct? It's a length that can't be negative. So we don't have to worry about the whole inequality thing of flipping signs. If I divide both sides by r, I get my ratio of arc length to the radius is less than 1. Would you agree with that? And again, if you were paying attention and you were watching for my mistakes, you would say, well, when you divide by a variable, don't you have to consider two cases? We learned about that in Unit 2, but like I said, in this case, no, because r has to be positive. It's a length. So does a, for that matter. Okay. Everybody okay with that? Doesn't make any sense, maybe. Like, that's not hard to understand, right? What it means, I don't know, but not hard to understand. Okay, what about this one? A and R. So here's my R. Here's my A. That length around the circumference, an arc is part of a circumference, right? I guess this is my theta in this case. Do you think A is bigger? Or this might be the easiest question you get in this entire course in all of grade 12 math. Is A bigger or smaller than R? Anybody? Help me out here. Go for it. Bigger. Everybody agrees? So again, if I divide by R, what happens here? The ratio of arc length to radius is greater than 1. Yes? We're just talking ratios here. Again, what does that mean? Who cares about this ratio? Well, we're getting to that. But in this case, the ratio of arc length to radius was less than 1. I don't know, half? 3/4? I don't know, 2/3? What does that look like? A to R. Maybe 2/3 of R, something like that. This one, A looks like 2 or 3 times the size of R. 3 or 4 times. What do you think is happening here? Anybody who hasn't peeked at the lesson in advance? Maya, what's our last option that's left? Equal to. Do they look about equal? Oops, I forgot to label R, A. They look about equal. I believe it. I made this with graphing technology, so I happen to know that they're equal because a computer did it. So I didn't just eyeball it and make them approximately equal. They actually are computer generated equal. But even if they're not, let's say they are. So A is not less than R, it's not greater than R, it's equal to R. So the ratio of A to R is equal to 1. There's my angle that I have rotated. Well, guess what? Theta equals 1 radian. In this case, that's the definition of a radian. So it's not arbitrary. I didn't just pick some number like 360 or 400 or 100 for that matter and divide the circle evenly. We talked about something natural in circles, the relationship between the radius and circumference or a portion of the circumference. And we came up with a unit of measurement based on that. If you do anything relating arc length to radius and the subtended angle, which is just the angle of rotation to define an arc, that's naturally in radians. To turn it into degrees, you have to multiply by some conversion factor, right? Now, you haven't really done that yet, but you can imagine that if you are creating some kind of machine that has a circular wedge, and you have to look at the relationship between how big the machine is, so how long the radius is, and what the angle is for the wedge, and therefore how long the arc is, that's in radians, just automatically. The relationship between radius and arc length is automatically in radians. To turn it into anything else, you have to convert. So this is why it's kind of called unitless. You might hear people say that, because you don't have to convert. It's naturally that way. So doing anything with circles, it makes sense. You're going to see that right away. Talking about circles and their properties is inherent in radians. But like I said, also in calculus in particular, which we don't really talk about in calculus, but maybe I'll mention it briefly. It makes our life easier. Okay. Any questions? So we've defined what 1 radian is. Kind of like degrees, you may not often think about what 1 radian is. So we tend to see other versions of radians pop up throughout this kind of trig that we're going to do. But that is by definition where it comes from. Like I said earlier, this ends up just being a very convenient way of doing things. It makes our life easy, so that's what we're going to explore and get into. And as I said also, from now on in this course, everything is done in radians. We never do anything in degrees. All answers must be expressed in radians. Don't convert to degrees and do the work that way and then convert back. We don't do that. If you have to do that in your head for the time being, that's normal. But eventually, you just work in radians. And again, if you're doing the practice, if you do all the practice and you're doing it and you're trying to do it in radians, you will. You cannot. It's like that analogy of language. If you are dumped in a country and immersed in a new language, within weeks, you can start to speak it. You learn it and you start to speak it without even really trying, just because by survival you have to. So you have to try to immerse yourself in radians and start speaking in radians. And within a few days, it happens that fast. You'll get better and better at it, and you won't even notice. At the end of the unit, I'll say, hey, by the way, did you ever notice when you stopped thinking about degrees? Because you don't even notice how often that happens. It just happens. You're just like, yeah, I haven't thought about a degrees in a week and a half. All right, number of radians and an angle can be found with the formula theta is equal to the arc length over the radius, that ratio that we were just talking about. What is the formula for circumference of a circle? We're going to explore some things that you already know and make some relationships, and then we're going to use those relationships to start thinking about radians in useful ways. So again, this is all kind of like made up. I'm guiding us here. This is not intuitive stuff that we're going to do, but it does tie into stuff you already know. Yep. Very nice. Most people say pi r squared, but what's pi r squared? Pi r squared is, yep, that's area of a circle, which jumps out in our head. And it's close. I like that. Just if I say something about a circle and you say pi r squared, well, you're on the right track. Like you're thinking something about a circle, but that's area. And I said circumference. So circumference is 2 pi r. So if I make an arc length that is a full circle, that means my arc length is a full circle, and it's 2 pi r. Okay? But if I want to use this to talk about radians and talk about an angle measurement, I have to divide by r. So I need this ratio of arc length to radius. So divide both sides by r. That means a over r equals 2 pi. I haven't done anything crazy here, right? Theta, my angle, is equal to a over r, that ratio. So this is my theta. What does that mean? I'm just going to make a little note here in case you're reading this later. What does that mean? Something very interesting happened here. How many degrees are in a full circle? See, I said the forbidden word. I'm allowed to. How many degrees are in a full circle? We just talked about this. 360. How many degrees in degrees in radians. How many radians are there in a full circle?
400.
That's gradians.
Oh.
So good answer, good for remembering, but radians, which is what we're focusing on now. 2 pi. Like this is the number. What's pi? Approximately 3.14. So 2 times that is approximately 6.28. So this is about like 6 and a bit. Just over 6 and a quarter, just over 6.25, 6.28 something. Okay. So this is a number, just like 360. But to you, it's a weird number. Why do we care that there are 6.28 and so on and so forth angles or whatever, like radians, but just like degrees in a circle? No, there should be 360 degrees in a circle. Because that's what you've grown up with. There should be 360. Why is it 2 pi? Or why is it 6.28? But again, I think you believe me that it's better, but that's what it is. So, therefore, we actually discovered something really important here. 360 degrees is 2 pi radians. So we often refer to radians when we're labeling the unit as RAD. As far as I know, there's not a better short version. There probably is in some circumstances, but that tends to be. But once we get into this, after we're doing converting, we don't define the unit anymore. We don't say RAD every single time. We just leave it. Okay. So if you're talking degrees, you need the degree symbol. If you're talking radians, we don't put a unit on the angle. Okay, because it is kind of unitless. It's a ratio, so we don't need it. But in this case, because we're converting, I'm going to put RAD to specify what I'm talking about. Does that make sense? Pi 3.14. This is a side note. What's the next digit? 3.14. Who knows?
1.
And then?
5.
And then? Yeah, you can't look it up on your calculator. 9 and then? 2 and then? 8? I don't actually know that one. I only know up to 2. What's the record? Anybody know? Don't shout it out if you know. This is so much fun to ask grade 9s because they have no idea. Like that was 3.1415928. So you got up to 7. Do you know more? Oh, okay, good.
It was 6.
Huh?
It was 6, not 8.
6. Oh, sorry, I didn't hear. I wouldn't know. See, you could have said anything and I wouldn't know because I don't know what the next one is. At some point, we all don't know what the next one is. So you know up to 7. You get kids in grade 9, like, so what's the world record? 10? Like 10. Yeah, in 10 minutes you could memorize 10 digits of pi. Like that's like a phone number. That's nothing, right? Anybody want to guess what the world record for memorizing pi is? 700. Okay, good guess. It's a lot bigger than 10.
I would say 123.
123. Anybody else want to guess? Throw out a guess. Random guess, Jackson.
3,000.
3,000. Okay. 150. Some people might say to Jackson like 3,000. Come on, you're gonna be kidding me. When I was in university first year, go ahead.
I was going to say, I know people that have done 250.
Right. So in the hundreds seems crazy, but it's actually not that wild. When I was in university, they talked about this guy who had it memorized to 10,000 digits, and he was some kind of memory guru or whatever. But even back then, I believe and I think the standing Guinness Book of World Record is still just under 70,000. So when you say 150, not even close. I mean, you say 3,000, you're like, come on, 3,000, that's ridiculous. No. It's still an order of magnitude bigger than that. It's still well over 10 times that amount. And there was a person who claimed to have done it to like 250,000 decimal places, but it wasn't held as a record for whatever reason. Guinness Book of World Records, you have to meet certain criteria, and it didn't count, I think. So I haven't actually looked it up, so you can Google it later. But last I checked, in the last few years at least, 70,000. And again, grade 9s are all like, what a loser, all they do is memorize numbers. Like, no. This is somebody whose brain works at a different level from ours. Like, it's not, at least from mine, it's not the same kind of thing. It's not even memorizing at that point. It's just a number that makes sense to them. Of course, they would have had to sort of sit down and study it, And there's no pattern in pi, as you know, so it's not like they recognize a pattern, but somehow they managed to memorize it. I'm going on a long time here. I wanted to cut this lesson short, but it's all really interesting stuff. There's this really neat documentary. I think it's on YouTube. It's called The Boy with the Incredible Brain. And it's about this boy who is in the UK. He's about my age, I think, so he's older now, but it was when he was in his early 20s they did this documentary. And he has he maybe has like autism, but he functions socially, doesn't come across as being on the spectrum, and also has this thing they think called synesthesia. And if you don't know what that is, again, you can look it up. It talks all about this in the documentary. And he describes how he understands numbers in a synesthesia kind of way, and how he recognizes pi. And he had the UK record for pi at 22,000 digits, and they show him in the video a little bit doing this and talking about it. It's pretty interesting. Anyway, but he could do it to 22,000 or something like that. So I think it was 22,000. Was it maybe just 2,000? I think it was 22,000. Took him like 5 or 8 hours or something ridiculous. Like, it's crazy. Anyway, okay, moving back to actual radians. It is related to pi. It has this natural relationship with pi. So you're going to see pi in everything that we do moving forward, almost everything that we do. And again, that makes sense because of the relationship between the circumference of a circle involving pi, which we already know, and the radius. It's a relationship between those two things, right? And so is a radian. So it's a natural connection that we have that. All right, now, what about a half circle? Divide both sides by 2. Would you agree that that's half a circle? So our arc length for half a circle, 2 divided by 2 is gone, is pi times r. So that's a half circle arc length. But again, if I want to talk about the degree measure, or not the degree measure, I got to stop doing that. The angle measure, we're going to do it in radians. We will relate it to degrees as well. Divide both sides by r. To get a half circle, our angle would be pi. How many degrees are in a half a circle? How many degrees are in half a circle? Arnhem?
180.
Now that's really important because, ooh, is that going to give me a circle? Good. That's an easy one to remember. You can remember that 2, and you will, 2 pi is a full circle, a full revolution. 2 pi is 360 degrees. But it's even easier, honestly, to remember that pi is 180. And if that's the main thing that you take away from this lesson, good. Everything starts at pi, everything starts at 180, and we can figure out what other angle measurements are from there in relationship to pi as like our anchor point. If I start with pi, I can work from there and figure everything out, which is what we're going to do on the next page, not in the next. We're going to do the first example first, but then we're going to get to the better activity on the back. Okay, very quickly. There we go. So there's a radius all the way around. Thanks. Windows. Take that radius, map it as an arc length onto the circle, so they're equal. That's equal to r. That's 1 rad, as we just talked about. This is just an animation showing us what we just talked about. So there's 3 rad, which is almost a full circle. Add a little bit more, you get pi 3.14. Two of that gives you a full circle, which is 2 pi. Okay. Any questions? All right, so very quickly, the conversion factor, which again, because this is not really what we're doing moving forward, you're going to do a bit of this today, and if you ever have to, you can fall back on this, like in your future or something. You always would fall back on the conversion factor, just like converting between centimeters and inches. What's the multiplier or divisor to convert? Same thing, we have one for this. There's also a trick, which I'm going to show you first. converting from radians to degrees, which only sometimes works, but most of the time. And that's kind of what you're going to do today, but we are going to eventually, like I said, get into not converting between the two. Okay, so I don't want you to think this is what we're doing. So 4 pi by 5. And the first time you hear that, that might sound weird to you, but that's very normal to me to say 4 pi by 5. It's how I would read that, 4 over 5 times pi, like the fraction is 4 over 5, but I would say 4 pi by 5, 4 pi divided by 5, right? Radians equals, how do I turn it into degrees? It says right here, replace the pi with 180. Now this is actually a trick that's a shortcut of what we're actually doing. But at any rate, it does work when there's a pi involved. So what is that? Somebody on the calculator help me out. My calculator's not working. Yep, Graham? 144. 4 times 180 divided by 5. 144 degrees. The homework does have some of that today, but again, that's not actually a useful skill moving forward. Oh, on that note, like I will never test you on this. There will never be questions on a quiz or a test that says convert the following. Like it's not a thing that we do, okay, to that extent. But like I said, we need something to do today when we introduce the idea of a radian, so this is what we're doing. To convert the other way, we multiply by the conversion factor, which is pi divided by 180, which is the ratio relationship between pi in a circle and 180 degrees in a circle, right, which we just kind of talked about. But this fraction gives you that conversion factor. So 130 degrees is 130 times pi over 180, which is 130 over 180 pi. And that kind of reduces to 13 over 18 pi, or 13 pi by 18 is how we would usually write it. However you think about it right now doesn't really matter, because you'll get used to the idea of it being written that second way, but that's how you would do it. And of course you would simplify it, you would reduce it, lowest terms. Again, because this isn't really what we're doing, I'm not too worried about the specifics of how do you want your answer written. Well, I don't. I don't want any degrees on your papers anywhere. Okay? Does that make sense? Is that okay so far? So just to go back, you can just watch. You don't necessarily have to write this down. You might want to if you want, but you could write it down after. What's actually happening here is I'm doing 4 pi over 5 times the opposite. Right? So one direction, I multiply by pi over 180. Going the other direction, I would multiply by 180 over pi, or divide by pi over 180. That's just normal conversion rules. And the pi's divide, and we end up with that. So that's why we use this trick of replacing pi, but what actually happens is the pi's cancel out when you multiply by the conversion factor. Okay? Like I said, there is a little bit of converting. You should know those formulas. There's a learning goal when you come into class tomorrow where you got to know those formulas. So learn them, but what we're about to do next is the biggest takeaway of starting to think in radians and understand radians. And some of you, many of you maybe, will already start getting it right away with this little activity. So this is big. Don't flip your page over. I hope it's everybody. Who remembers what pi is in degrees? Oh, flip your page over, not that side, the other side. Yeah, flip it over to that side, not the first side. Don't cheat. Do you remember what it is? Pi is how many degrees? Yeah, Mohammed. 180. So what's pi by 2? In degrees. 90. How'd you get that? Just divide it by 2. Replace the pi with 180. Divide by 2. What's pi by 3? Jackson? How'd you get that?
180 divided by 3.
180 divided by 3. See how easy it is? 60 is a normal measurement that we see in triangles. 90 is a normal measurement that we see in triangles. In fact, those are both in the special triangles. So pi by 2 and pi by 3 are angles we're going to see, but in radian measure. And if I see the angle pi by 3, how do I know that means 60 degrees? Like, how do I know what it means? Well, if I know pi is 180, then I can figure out that pi by 3 is 60. But eventually, like I say, you don't do that translation, that conversion in your head. You just think of pi by 3 itself. Pi by 4.
45.
How'd you get that?
180 divided by 4.
180 divided by 4. Can you do it a different way? Anybody do it a different way? I did it a different way.
I just do 90 divided by 2.
90 divided by 2. And these are not one way is better, by the way. It's different. Okay, so if I did it a different way, that doesn't make it the better way. But we do start thinking in fractions at a deeper level if we start doing it multiple ways. And if I take pi by 2 and I want to turn it into pi by 4, how do I do that? Divide by 2 again, which means multiplying in the denominator by 2. So 2 times 2 is 4, divided by 2 again. And 90 divided by 2 is something I can do easily to 45, whereas 180 divided by 4, that might not be something that jumps out at you, where you know what that is. Just like what's 180 divided by 8? But 45 divided by 2 is 22.5. That I can do in my head, which means pi by 8 would be 22.5. Right? So this is where we start to actually think in fractions and do fractions. There are multiple ways of doing it. And you kind of want to get used to all the different ways of thinking about it. So take pi by 2, divide by 2 again, gives you pi by 4. 90 divided by 2 is 45. Pi by 6. Graham?
30.
How'd you get that?
3 divided by 3.
Oh, nice. So 60 divided by 2 is 30. Pi by 3 divided by 2, I add that 2 by multiplying to the bottom, right? So it's half of pi by 3, or it's 1/6 of pi. That would be a normal thing to go 180 to 30 is dividing by 6, so that's how you get there. Pi by 9. Those are very common ones, by the way. We're going to see them all the time starting tomorrow. Pi by 9, not so much pi by 12 eventually. We'll see a little bit. In fact, pi by 9, not really at all. I don't know why that's there. Something to do, I guess. Pi by 9 is, who's got it? Yep. 20. So you could do what? Pi by 3 divided by 3, or pi divided by 9 is 20, right? Those are all easy to do. Pi by 12? Graham?
15.
How'd you get that?
Pi by 4 divided by 3.
Nice. Pi by 4 divided by 3, or pi by 6 divided by 2. Like again, there's relationships there. There's different ways of thinking about it. Or pi divided by 12, 180 divided by 12. You might need to pull your calculator out for that, though. You might not, well, I mean, you could do it in your head, but that might be where you just want to punch it into your calculator. Okay? But I could do that in my head maybe by using one of those other shortcuts. Okay, starting back at the top, pi is 180. There's no trick questions here, folks. What's pi by 3 then? Once again, we just did this. 60. So what's 2 pi by 3?
120.
How'd you get that?
Multiply by 2 divided by 2.
So this is literally 2 pi by 3s. It is also 2/3 of pi. I could take pi, which is 180, multiply by 2 and divide it by 3. 180 times 2, well, that's 360. 360 divided by 3, well, that's 120. 36 divided by 3 is 12. Like, I can do that mental math, but I know pi by 3 is 60, and now I have 2 of them. That's 2 60s, which is 120. That's how my brain starts to fire in doing these conversions. And again, this is where you really start thinking in fractions. Instead of 2/3 as a fraction, it's 2 1/3. Right? So 3 pi by 3 is, Graham?
180.
180. How'd you get that? Well, it's equal to pi, because 3 divided by 3, they divide out, and you get pi. And again, of course, we're talking fractions. We're going to be reducing fractions. So 3 pi by 3 is pi, which is 180. But also, sometimes when we're counting in fractions, we count 1 pi by 3, 2 pi by 3, 3 pi by 3, 4 pi by 3. We're actually counting in those. So if you're writing it down, I would reduce it. But if I'm just counting in my head, I go 1, 2, 3, 4 to 4 pi by 3s. Speak of the devil, 4 pi by 3. Say again? 240. And we recognize that maybe from some of the angles that you did in grade 11, 240 pops up, 225 or 210, these different ones pop up here and there, right? So again, they're going to be the same kind of thing here. But are you just now counting by 120 basically? Okay, so 120, 240, or counting by 60s, 60, So 6, 12, 18, 24, and so on. So 5 pi by 3 is going to be? Yep, Harnum.
300.
And 6 pi by 3, well, that's reducing is 2 pi, which is 360, which is also 5 pi by 3 plus 1 pi by 3, which is 300 plus 60, which gives me 360. But when I'm adding fractions, I add with the common denominator. So if I have 5 pi by 3s, I add 1 pi by 3 to get 6 pi by 3s, which is 2 pi. That gives me my 360, which is a full circle, which we've already talked about. See how this works? Why didn't your teacher in grade 3 teach you fractions like this? You probably couldn't do it in grade 3. All that work in grade 9 you do with fractions, and it's fractions like 5 over 17, and it's like, oh my gosh, like what is that fraction, 5 over 17? It's nothing. But when we talk about these easy fractions, like 2/3 and 4/3, and start to really count by them, it starts to make sense. Okay, let's finish off the next two. You probably kind of see the pattern of where this is going. 180 divided by 2 is 90. So 2 pi by 2, again, that's a full pi, which is 180. So what's 3 pi by 2? $90 is 1 pi by 2. 180 is 2 pi by 2. 3 pi by 2 is 270. Do you recognize that? Isn't that one of the splits of the quadrants? Quadrant 3 and 4, that's where your 270 is, so that's 3 pi by 2. 1 pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, which is 2 pi by 1, or 2 pi, or 360. Pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 2 pi. Full circle. Angles in standard position. That arrow that I drew, mapping out how far I've rotated, is actually a full circle. So its length should be 2 pi, shouldn't it? Times the radius, like in terms of circumference. Okay, last one, 180. What's pi by 4? Pi by 2 is 90. Half of that is 45. Pi by 4 is another common one. It's in one of our triangles, right? So pi by 4, pi by 3, pi by 6, those are in our triangles, come up all the time. So what's 2 pi by 4? It's 2 45s.
90.
I can reduce the fraction, or I can just say it's 2 of a single pi by 4, and a single pi by 4 is 45, so it's 2 of those, so it's 90. Right? Again, neither one is better or worse. They're different ways of getting to the same place. You kind of want to be able to do both. So what's 3 pi by 4s? 45, 90, 135. 4 pi by 4s, that's pi, so that's 180. Isn't that a whole? That's 1 whole pi, which is 180, so that's a halfway around the circle. Again, when you see that whole, that's big. I know, like I have that pivot point or that anchor point that I've got to. What's 5 pi by 4? 225. 6 pi by 4. Yep. 270. So that's 3 pi by 2, which is 270. Again, different ways of thinking about it. 7 pi by 4, just counting by 45s here, so 315. And 8 pi by 4, that's 2 pi, that's 360. That table, to me, is where you are starting to think in radians the way that you should be. And the most helpful way of sort of learning to count in radians, which we will do when we scale graphs, and that you will do to some extent, you will do in angles in standard position as we count around the circle, like you're going to be counting this way. Okay? So very, very useful. And notice how it all stemmed from 180. Each one of those columns started at 180, and we kind of figured out from there. So you can always fall back on 180. If you get a weird one, 11 pi by 6. What the heck is that? You can start at 180 and go from there. It's 11 pi by 6s. Okay? So we'll talk more about that as we go over the next few days, but that's the kind of thing that if you don't believe me, trust me, you will get there, believe it or not, without even trying. If you're doing the homework and if you're thinking about it, it just happens. Okay, a couple of questions. One more question that we're going to do together because there's a couple in the homework, and this is the kind of thing that textbooks sometimes have questions like this, or if you do engineering and start talking about circles, you would start with questions like this, but we don't actually explore much of it in this course. But it is in the homework today. Determine the angle made by an arc length of 5 centimeters in a circle with a radius of 8 centimeters. So all of these questions start, oop, that did not give me a circle, a little bit closer, there we go. Start with a diagram and just thinking about the relationship between A and R. You just have to be careful about what your A and your R actually are. So I'm going to draw this since I don't have a diagram. In the homework, it gives you the drawn out circles. You don't have to draw them yourself. So we have a radius of 8. And we have an arc length of 5, so that's less than 8. So I'm going to just, maybe a little bit bigger than that so that I can kind of write in this thing, but try to make sure that it is less than. So here's my arc. I suppose there could be some little tricks where like radius is in one unit and the arc length is in a different one. I don't think that's on the homework, but like it could be in millimeters and centimeters or something. But anyway, these are all in the same unit, so we're fine. So we talked about this. Theta is the ratio of the arc length to the radius, which we know. So this seems like a totally uninteresting question. That works at 0.625 radians, or leaving it as a fraction, 5/8 radians. There's no pi involved because we didn't start with 180. It just doesn't happen to have a pi in it. But this is still a number. Remember, pi is just a number. Pi by 3 is 60. 180 divided by 3 is 60. Pi by 3 is 60. And pi divided by 3 is about 1. It's a bit more than 1. 3.14 divided by 1 is a bit more than 1. So 1 radian, right, you can kind of visualize, is around 60 degrees. But we don't often talk about 1 radian. We talk about pi radians, or pi by 3 radians, or pi by 2 radians. Okay, but in this case, 5/8 radians, because we're talking about a circle, that comes up to, that's in the homework today, but after today in this course, not so much, but I can imagine maybe in other places. Some of the questions, by the way, give you A and theta, or give you R and theta, and then you have to find A, like they're not all this easy. This one gave us A and R, so we just divide to come up with theta. I'm going to let you try those two on your own. Same with those. It's just doing the same stuff, doing the trick from the last page. But you don't need my help with those. You can check the answers online, or I'll put them up in a minute. Otherwise, that is radians. Any questions? It's a big deal. I'm going to say it again, and I'm going to say it again tomorrow and the next day and probably the next day and maybe every day for the rest of this unit. Quizzes and tests are not allowed to have degrees on them. I'm not going to ask you to convert. Okay? And I don't want you converting, doing the work in degrees and converting back. If you have to do that in your head, that's fine. I can't stop you from doing that. But all the work you write on the page will be in radians. And I only encourage you to start trying to do it in radians. And if you do and you're doing the homework, it just happens naturally. You will be able to do it in radians. You won't have to convert back to degrees. If you get to the quiz and you're still thinking about degrees, I would say, have you done the homework, like rigorously? Because maybe you didn't. And the other thing, I said this the other day, but if you weren't here, or just as a reminder, that quiz where we're doing this is a no calculator quiz. So you have to be able to convert between 180 and 60 pi and pi by 3, like without your calculator, and do it on your own, which also means thinking in radians, not converting. So keep all of that in mind. That means you should be practicing without your calculator. There are some questions that require a calculator. Obviously, you pick up a calculator for those. But special triangle questions, stuff that you can do without a calculator, you should be already trying to do them without a calculator. Check with a calculator, sure, or check your answers online, but try it without a calculator.